स्टूडेंट्स आपको आवाज आ रही है बेटा?
Yes, yes, sir.
Okay. The topic of today's lecture is acid-base properties of amino acid. In last lecture, we discussed what are amino acids, what are their structure, and now their properties. The amino acid usually is ionic, and their ionic character depends upon the pH of the solution in which you are putting them. Here at the bottom, you can see the uncharged amino acid structure. This is the general structure of amino acid as we discussed last time. So if you see here, this one is carboxyl group, right? COOH, carboxyl group. And on the opposite side, you can see NH2. We call it amino group, right? And in this case, they have no charge. There is no charge on visible in here. But they can convert to this condition where this COO here get the negative charge and NH3 gets the positive charge. How this happen? This we need to understand. As you can see here, the carboxyl group loses a proton, giving a carboxylate ion. Here you can see this proton is removed, and here carboxylate ion is formed. So you can see this negative charge because of the removal of one proton. And the amino group is protonated to ammonium ion. This amino group is protonated, receive the proton, and it get positive charge, as you can see here on the top of N. So this carry negative and positive ion, which is called dipolar ion or Zwitter ion. So Zwitter ion, the amino acid, the molecule contain both positive and negative charge. The dipolar, this positive and negative nature help them to react and make the larger molecules. And also this dipolar nature give the amino acid unusual properties. Unusual properties mean the properties which make them different. Let's discuss some of those properties. Here the amino acid have high melting points, generally over 200 Celsius. This is the glycine, the simple amino acid. Its melting point is 262 Celsius. That is very high. You know, 262 is very high temperature, right? You know, at 100 Celsius, water get boiling. So the 262 is too high temperature. The melting point for glycine is 262. So this is their unusual behavior that the amino acid, they have very high melting points. Melting point is the temperature at which molecules start melting, right? And this melting point for glycine is 262 Celsius. Another unusual property of this amino acid is the dipole movement. The amino acid have larger dipole movement than the simple amines or simple acids. Dipole movement is the measure of polarity. As you can see, its unit is divide, we represent with D. Here we take the simplest amine like amino acid, glycine. The dipole movement is 14 dBi. However, for simple amines like propylamine, the same dipole moment is 1.4, which is very less than 14 dBi. And of course, it is very different from the simple acids as well. Like you can see here, the propionic acid has the dipole moment 1.7 dBi, which is of course very less than 14, which the simplest amino acid glycine bears. So the amino acid, they have larger dipole moment as compared to the simple amine or simple acids. And very interestingly, the amino acids are more soluble in water than they are in organic solvents like dichloromethane, ether, for example. The amino acids are more soluble in water. You know, the organic solvents, they are usually they bear the good properties to dissolve something. But in case of amino acid, the amino acid are ionic, as you have discussed earlier. And the ionic can be soluble more in ionic solvent like water. But organic solvents are not ionic, so they cannot solubilize amino acid. So the amino acid are more, we can say, soluble in water than they are in the organic solvents. So dear students, can you hear me?
Yes, sir.
Yes, sir.
Okay, good. So here, amino acids are less acidic than most carboxylic acids and less basic than most amines. In fact, the acidic part of amino acid molecule is the NH3 plus group, not COOH group. The basic part is COO negative group and not a free NH2 group. What does it mean? What is acid? Acid which have ability to give proton, and base which can receive the proton, right? Right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, so if we have COO negative, which means it has donated proton already, right? if this COO negative already have donated the proton, now it can receive the proton and cannot donate more proton, right? If this can receive the proton, this means it is base. Usually COOH is acid, right? But COO negative, it can receive the proton, the which can receive the proton is called base. So COO negative is base. Usually the mine is base, but in here this can donate the proton, this NH3 positive, right, can donate the proton, and if it can donate the proton, it is acid. So this NH3 is NH3 positive is acid and COO negative is base, which is different from the other cases, like where we find the COOH, we call it acid, but where we find NH2, we call it base group. But here it is opposite, it is different. Here COO negative can receive the proton, so it is base, and NH3 positive can give the proton, so they are acid. And we call them amphoteric because these amino acids contain both acidic and basic group. As you can see here, they can have both acidic and basic group. So this property we call the amphoteric property. And here is very interesting property of the amino acid, that the predominant form of the amino acid depend upon the pH of the solution. If you have acidic solution, this bear positive charge, and we call it cationic state. But when they are in basic solution, they carry negative charge. So the pH of the solution is very important, and this determines the charge on the amino acid. That's why we say that the predominant form of the amino acid depend on the pH of the solution. Here in this equation, you can see in the middle, the blue text, you can find it is written neutral. On the right side, it is written anionic in base. However, on the opposite side, left side, it is written cationic in acidic solution. So how this charge change on amino acid, this is the aim of this. To understand this is the aim of this slide. Here you can see this is neutral. This is the general structure of amino acid. Here is the carboxyl group, here is the amine group, and here is the R. And here is in center alpha carbon. This COO negative, right? If this COO negative receive the proton, as you can see here, if we go in this direction, please look this arrow, the arrow given below, which represents the proton, H positive proton. If this neutral amino acid receives this proton, then this COO negative becomes COOH, as you can see here. And this negative charge disappears. Now this COO negative convert to the COOH after receiving this proton. Now look at this NH3 positive. This carries the positive charge, so we call it cationic state. And when this is possible? When the solution is acidic, right? When the pH is very low, around 2. When pH is around 2, this get cationic. The same neutral amino acid convert to the cationic state when it is in the acidic solution having the pH around 2. And now see its reverse case, like cationic state to neutral state, how this amino acid converts. You see here, now you need to look at this OH negative. In this case, the same carboxylic group COOH will release this proton, which will join with OH negative and make the water. And now when this is removed, this COOH convert to the COO negative. And this negative and positive is equal, so this is neutral amino acid. And what is this actually? OH. This is actually the addition of base, right? So this means this is the acidic condition where pH is very low, but when you add OH negative, mean the base, you get pH higher and higher and higher. And if you continue the addition of this OH, as you see on the right side of this equation here, this neutral convert to the anionic, mean negatively charged amino acid. What happened in this case? You are adding this base, and this OH negative need proton, and this COOH will not give the proton. This Na3 positive can give proton, and that proton will react with this OH negative and make water molecule. And if this Na3 positive donate the proton, then this convert into NH2 positive, as you can see here. And this amino acid overall get negative charge in here. Because this Na3 positive donated the proton, there is no more positive charge in here on NH2 positive. So we get the charge on COO negative. So this is anionic state. And when this amino acid gets this state, when it is in basic solution, the pH value is around 9 to 10, right? It means very high pH value. So on this side, you have the basic condition. On the other side, you have acidic condition. And from neutral to, if you add more and more and more base, then the same zwitterine of the amino acid, the neutral amino acid convert to the anionic, negatively charged amino acid. And if you see this reaction changing this anionic state of amino acid to neutral, how this can happen by the addition of this proton, right? When we have this anionic and we reduce the pH by adding the acid, this proton join here and this NH2 convert to NH3 positive. Now by addition of this proton, this anionic convert to the neutral state. Now this amino acid carry negative and positive both equal charges. So it is called neutral state of the amino acid. Now from this you can conclude that if you lower the pH of the solution, amino acid get positive charge, as you can see here. And if you have the basic solution, it changed to the anionic state. This is the reason we call that the dominant form of the amino acid depend upon the pH of the solution. So here in the titration curve of the glycerine, the same concept is explained in detail for better understanding. Can you see this figure on your desktop, beta?
Yes, sir. Yes, sir.
Yes, sir.
Okay,
Yes, sir.
good. Okay. So this is titration curve. And you have to understand the change in ionic state of this amino acid by changing the pH value. Here you can see the positive charge on the glycine, and the pH value is around 2.3 here. In this range, if you have the amino acid in acidic solution, the acidic solution which bears the pH value up to 2.3 or less than this value, then your amino acid is in cationic state, carrying the positive charge. Right? And if you increasing this pH value, then this positive, you can see here, you get the negative charge as well here. How this COOH will donate the proton as the pH increases, and at pH 6, the zwitterine, this amino acid bears the both charges. How this OH, COOH will donate the proton and will convert to the COO negative. So in this state, this amino acid bear both positive and negative ions, which is called zwitterine. And this point where you get this positive and negative charge on amino acid is the isoelectric point. And here you can see the isoelectric point for glycine is 6, where the glycine bears negative and positive ion, which is called the Zwitter ion. And if you increase the pH value even more, then what happens? This Zwitter ion convert to the anionic state, mean negative charge on the COO only you will get. How? This NH3 positive will remove the proton and convert to NH2, which will not bear positive charge anymore. Now on this same glycine we have negative charge. We call it anionic because of this negative. And how this happen? When you have high pH value above 9.6 pH, you get this negative charge on the glycine. So this is the reason we usually say, if we will have the amino acid in cationic state below the pH value 2.7 and the Zwitter ion state at 2.3 to 9.6, from this to this range we have the Zwitter ion mostly. But you need to understand that the anionic state we get above 9.6 behind this. So as you go beyond this isoelectric point, you start changing towards this anionic state, mean the amino acid will carry only the negative charge. So here you can see pKa1, first dissociation constant, acidic dissociation constant, where this will remove first proton. As you can see here, this will remove this proton from COOH. And pKa2 is the second dissociation constant, where this glycine remove the second proton from NH3 positive and convert to the anionic state, as you can see here on the top. So from this you understood that the state of the amino acid depend upon the solution pH, the pH of the solvent, right? So from this we understood that by varying the pH of the solution, we can control the charge on the molecule. This ability to control the charge of amino acid is useful for separating and identifying the amino acid by electrophoresis. So next we will learn what is electrophoresis. Dear student, do you have any question? Now we will discuss isoelectric point and gel electrophoresis. To study the isoelectric point, you must need to understand the basic concept that an amino acid bears a positive charge in acidic solution and negative charge in basic solution. So the pH is very important. It will of course change the charge on amino acid. There must be an intermediate pH where the amino acid is evenly balanced between the two form, positive and negative, as the dipolar deuterium with net charge of 0. Actually, this pH is called isoelectric pH or the isoelectric point. Please look at this central structure. This is the amino acid structure. Here you have carboxylate ion and here you have ammonium ion. Here negative charge and here positive charge, they will cancel each other. The overall charge on this amino acid is 0. The net charge is 0. So it is called neutral. If you place this amino acid in acidic solution, then this will get the positive charge overall. How? Because this carboxylate ion will be pH value is 9.7. Now, if these amino acids are placed in the solution having the value pH value 6, then what will be charge on these amino acids? In this scenario, you must need to understand that this alanine is at its isoelectric point when the solution pH is 6. And the overall charge on alanine will be 0. So it will be neutral in solution having the pH value 6. However, the pH 6 is more acidic than the isoelectric pH for lysine, that is around 9.7. So lysine in this solution will carry positive charge. However, the aspartic acid has an isoelectric pH 2.77, we can say 2.8 as well. This aspartic acid having the isoelectric pH 2.8, it will carry a negative charge in solution having the pH value 6. So here we explain the same concept, that amino acid isoelectric point and pH effect and contribute in the gel electrophoresis, and how it is helpful in the separation of amino acid mixture. Gel electrophoresis actually uses the difference in isoelectric points to separate the mixture of amino acid. Please look at this image. You have here the power supply. This is the positive and connected with the electrode, and this electrode we call it, because it is positive, so we call it a node, and here is cathode. And here between the electrode you have acrylamide gel or filter paper. And the solution here have the pH value 6. So you need to remember this. This is very important. And here you have a stick having the mixture of amino acid, for example, alanine, lysine, and aspartic acid. Now, when you apply the high voltage, then what will happen? Then it's very simple that the opposite charge usually you can see here in this image, the lysine and aspartic acid in buffer solution lysine, aspartic acid, and alanine all are in solution having the pH value 6. The alanine alanine is at its neutral point, have no charge. When it is placed in solution having the pH value 6. But pH 6 of the solution is much acidic for the isoelectric pH of lysine, that is 9.7. So lysine is in the catonic form. However, the aspartic acid has an isoelectric pH 2.8, so it is in anionic form. So when you apply the voltage, they will move towards the opposite charges. This lysine carrying the positive charge will move towards this cathode. However, this aspartic acid carrying the negative charge will move towards the anode. And this alanine will not move. The reason, it is not carrying any charge, so there will be no attraction from cathode or anode for this. The resultant, there will be After a period of time, you can recover the different amino acid from the gel or the wet paper. Now, if the electrophoresis is being used as an analytical technique, I mean, you want just to determine the amino acid presence in the mixture, then the gel can be treated with the ninhydrin to make the band visible. And later, these amino acids can be compared with the standard and can be identified. In next slide, we will see how the amino acid react with ninhydrin to produce a visible color. As you can see here, this is the ninhydrin. This react with amino acid in the presence of pyridine. It makes the remnants purple color. And this romance purple gives the purple color to the mixture. And this technique can be used to track the criminal people and to find the fingerprint. For example, if a kidnapper touches a ransom note with his fingers, the dermer ridges on his fingers leave traces of amino acid from the skin secretions. The treatment of paper with ninhydrin and pyridine cause these secretion to turn purple, forming a visible fingerprint. So, using this technique, you can track the criminals, and this will be helpful for the criminals